This is Free Range Digital Design Foundation Modeling, Chapter 25. What we're going to be doing in this chapter is more state machine stuff, still kind of an introductory mode. Hopefully we will get to using state machines as controller circuits. That's what we'll see in this chapter initially, and also as sort of a build-up to it, we'll be working with sequence detectors. Now, the approach we're going to take in this chapter is to start with some basic, very simple circuits and then move up to circuits that actually need FSMs to be controlled. So the initial problems are just blinking LEDs. Later we'll get to sequence detectors and less timing issues in general. And finally we'll do a couple of control problems. Most of the control problems will come in the final 3 or 4 chapters here. So keep in mind that state machine design, doing 9% of the work, is generating the state diagram. The state diagram has all the intelligence in it. Once you have that state diagram, it's almost trivial to implement that somehow. Essentially, I'll say implementation approaches are relatively cookbook. So once again, the tough step is generating the state diagram. But we should talk about like a brief history of controlling circuits, since that's what we're moving towards pretty much this entire book. So a long time ago, the issue was you needed to control the circuit with something. Computers were expensive. You know, there weren't computers out there doing things, so people would design essentially state machines to control their circuits, to handle their circuits' control needs. Essentially use flip-flops and logic on discrete ICs. It wasn't too advanced. So later ICs came along. ICs are integrated circuits, just means a chip with a bunch of different stuff on it. Essentially integrated circuits came along and took care of some of that control instead of using discrete hardware. And now the things that come to mind are, first, a display multiplexer for 7-segment displays. Now it's very easy to do with discrete hardware, but if you have a chip that does it all for you, you have one chip doing all the work rather than 5 or 6 or 8 or 10 on your board to do the work for you. The ICs really helped out, lowered the chip count, gave a lot of functionality. And later, PLDs came along. The PLDs were programmable logic devices. Initially, these devices had, like they said, they just had logic on them. And later they came in with sequential circuits, and modern day PLDs have entire computers on them, computer cores, as well as typically fabric of a PLD, which allows you to implement a bunch of logic. Very, very powerful. Lastly, in the modern day here, is you have to control your circuit with something. Microcontrollers are very cheap. There's a bajillion different types out there. One is certainly going to fit your needs. The only difference this chart is here is that microcontrollers are software control or firmware, however you want to say it. All the other devices we're talking about is hardware control. So in this course, we're 100% interested in hardware control. So in the end, we've described all these methods here. The idea here is you're not limited to using only one of the methods. You can use anything, as many as you need to get the job done. For instance, you could have a microcontroller controlling your circuit as well as some external hardware, maybe a math coprocessor, or just a programmable logic device handling some of the logic to lessen the software needs. So whatever you need to do, you do it. And when you get to that point when you're doing that, you'll understand all the parameters. So we're not quite there yet, but yeah, this is not, you only get to use one. The idea is you're the designer, you get to make the circuit work. Quick overview of design approaches so far. We've had circuits with no control. We've had external control, and now we are working towards circuit control, which is necessarily a state machine. And we've used all 3 design approaches here. Brute force design was the first one we learned. It's very limited in the number of inputs, but we've done it in quite a few problems, and of course they had 4 or less inputs. We also used iterative modular design. We haven't really used that much outside of the parity generator, ripple carry adder, and comparator. But mostly where we want to be is in modular design. That's where we spend most of our time, and essentially that's where we want to be because it's very efficient, but we can always back up a few steps to go back to brute force design or iterative modular design if necessary. Here is our first example problem. Essentially, I'm going to blink an LED at half the clock frequency of the input clock here, and this is what we see here. And what I need to do for this is just provide a state diagram. Nice of this problem, it already has provided a black box diagram. So this circuit, what I need to do is, it's just really a standard circuit. It's kind of a trick. Once you see it, it works. You'll never forget it. And so essentially what I want to do is I have a waveform that looks like this, and what I want is an LED that looks like this. The notion here is this is one period of the LED, this is two period of the clock. Now that means I've cut the clock frequency in half on this. So I get a clock edge, I turn the LED on, I get a clock edge, I turn the LED off. Now this is a very standard state machine design. It's two states. All I need to do is go from one state to the next state. So these are the states, the transitions. There's nothing controlling these transitions here, so I don't see any inputs there. And all I have to do is state when the LED is on and when the LED is off. And there it is. Another way to do this is to say LED equals 0, but we'll leave it at that. This is the state diagram. There are no clock signals, of course. I'm going to check this over. I've handled each output there. There's no inputs to mess with the transitions, and I'm going to call this problem done. It just goes from state to state every clock cycle. Every input clock cycle goes from one state. Next clock cycle goes back, and you can see it goes from the LED on state to the LED off state. This is the example timing diagram here. As you can see, here's the clock frequency. This clock edge is going to cause a transition. Every clock edge is going to cause a transition because all the transitions are unconditional. And you can see the LED going on and off and on and off. And most importantly, once again, you can see that the LED frequency is half the clock frequency. This is a problem, looks similar to the other one. What it's doing is it has a button there. So let's see what the button's doing. It has a 50% duty cycle when the button's not pressed. When the button is pressed, we'll say it prevents the LED from changing status from on to off. There's an associated timing diagram, but we're not going to worry about that. And so essentially what we have here is an external input. That external input is going to control the transition. Let's just draw this. Look, and look, the LED, there's only two states. One input, there's two states. The LED is on or off, so we can draw that, without knowing what we're doing. LED it will say one way to do this is just to take one input at a time. Now there's a button, which means we need to account for two arrows leaving each state. So that's the arrow associated with the button on, arrow associated with the button off. So let's look at this. Okay, when the button's not pressed, it has 50% duty cycles. So we can just put that in there. So if the button's not pressed, this problem is exactly like the last problem. But what happens when the button is pressed? No changes happen. So we're going to put that in like this. Self loop, so if someone presses the button, it stays in that given state. And essentially that's all we need to do for this problem. Here's an associated timing diagram. You can see if the button's pressed, you can see it's not going to change state. So it didn't change state there. And that's because the button is pressed. So the only time it changes state when the button is not pressed. And so here's the button that's not pressed. You can see that it went from LED off to LED on. And you could probably see that happened somewhere else here, LED on to LED off. So once again, here it's pressed, which means it doesn't change state. So here is a example problem that has something to do with the duty cycle. And so we've been working with 50% duty cycles, 33.3% duty cycle, which is pretty much obviously a 1/3 duty cycle. And so also what I need to do in this problem is state some frequencies here, and I think I need to provide a frequency of this clock. What we want is the 33.3% duty cycle at 60 megahertz. So let's just draw this real fast. And it has no conditions here, so it's all the conditions are unconditional, all the transitions are unconditional. There's our problem, and we can actually better put the LED in there. That means for one state, the LED is on, it's off for the other two states. So this is going to create the required 1/3 duty cycle. And so the other issue in this frequency is at 60 megahertz. We better draw this. I laugh because I never know how to do these. I just kind of wing them. Okay, so it's going to look like this. This is what we have here. And so this is 1, 2, 3. This is 3 clock cycles. This is three clock cycles, and this is the timing associated with 60 megahertz. That means there's a period here. This is the period of 60 megahertz. So we'll just put t equals 1 over 60 times 10 to the minus 9 hertz. Yep, got that wrong. 10 to the 6 hertz. And so if that is period of 3 of these, 1/3 of that is going to be 1 over 60 times 10 to the 6. That's 1 clock cycle. We're going to divide that by 3. Okay, so this will make, we'll make this t sub x. So this is going to be t sub x. So it's this period divided by 3. Finally, the frequency of this clock here needs to be. So I'm going to call this problem done. Once again, I don't feel like breaking out a calculator, and that's okay. Just set it up and it looks good. So the important thing is this gave me the 1/3 duty cycle, and I had to go look at this thing to get that proper clock frequency. So the desired, this was associated with 60 megahertz, and I needed to figure out what the actual clock frequency was, which is, I think it's going to be, by the way it's set up, it's going to be 3 times this clock frequency. No surprise there. Here's the associated timing diagram. You can see that 1 cycle it's on, 1 and 2 cycles it's off, and so that's our 1, 2. That's when it's off. Looks good, and works good.